So this is when I have a hydrogen sample, our velocity profile in the cold region, only in the cold region. Don't forget, only in the cold region. Okay, and our function is like this. Our velocity is like this. Okay, only apply to the cold region. And if you plot like this flow, okay, I have a pressure wave like this. This is our pressure gradient with a cosine nt function. And remember, in the cold region, our flow is what? Our flow is a sine nt function, right? And this is a dash line here. So our flow with the pressure gradient has what? Has a phase delay. Okay, 1/pi/2 phase delay. So as you can see here, this is our pressure is higher. However, our flow is almost zero. And when the pressure gradient is zero, we have a measurement velocity. Okay, we have measurement velocity. And when the pressure is a negative, okay, it's a measurement in the negative. But however, our flow is a minima. Okay, our flow is a minima here. Okay, and then when the pressure go to zero, pressure gradient go to zero, partial P partial is equal to zero here. And we get a negative measurement velocity. So I have this kind of flow. Okay, in the cold region, if I plot the center velocity profile, center point velocity with time, this is become like this. So as you compare with these two functions, this is a cosine function, this is sine function. So that means we can go back to here. Okay, our flow is pi/2 out of phase with a pressure gradient, right? Because the pressure is higher, pressure gradient higher, we have a phase lag. Okay, and as you can see here, for this term here is a sine cosine function, and this term is what? Since the px is a constant, okay, n is also constant once you fix the frequency. So this is constant here. So this constant means what? The flow didn't change with y direction because there is no y function here. Okay, and that means what? Our flow almost what? Almost is flat in the cold region. Okay, that means the flow change with y is very small, change with y is very small, change with y very small, change with y very small. We didn't, in the cold region, the flow didn't change with, there is not a y function anymore. Okay, so that's another indication here. For this approximation solution for hydrogen sample, we can have this. This is the amplitude of our flow, right? Change with sine function, and this amplitude is a constant. Okay, amplitude is a constant. Okay, but sine cosine is a change, right? Because so here is this constant mean it's not function of y, so it's uniform. Okay, the flow is uniform, more close to uniform. Okay, next let's define the so-called boundary. Okay, extend this. If this term here is not if our flow is within the boundary layer, within the thin boundary layer. Okay, within thin boundary layer, that means y/a is equal to 1 minus order of the random sample, square root of random sample, because this is our what? This is our random sample thickness. Remember, in one of our homework before, right? Our delta is proportional to what? Square root of random sample over 1, right? So that will be, in this case, very similar. Okay, this is the boundary layer thickness is 1 over square root of random sample. Okay. 不知道大家还记不记得 One of our homework before, okay, we try to study what? The boundary layer thickness, right? This is a flow over a flat plate. And then we have a boundary layer, and this boundary layer will be flow the thickness delta, okay? And this is velocity profile, different excitation. Okay, this is our boundary layer thickness. And delta is proportional to what? Remember that in our homework. The thickness is okay. So that will be very similar here, okay? This is our boundary layer thickness. So as you can see here, okay, one mass this term here is order of what? One is order of Reynolds number, square root of inverse of square root of Reynolds number. Times this Reynolds number, what happened? This one and this one will be multiplied together, will be approached to 1, right? It's order of 1. So that means this is not a small number anymore. This is not its potential decay anymore for this within the boundary layer, right? So within the boundary layer we have a different, okay? So if you see the picture here, we have a flat uniform velocity in the core region here. However, within the boundary layer here, okay, within the boundary layer region here, there is a function of y, right? This is a function of y because this is almost flat, and this is a function of y. This is a function of y. So within the boundary layer, okay, you have to take into additional account. Okay, you have to discuss near the boundary layer region. In the core region is much easier because we have a core region solution like this. This is near the core region. Okay, and within the boundary layer is different. Okay, slightly different because this term here multiplied this term is the order of 1. Okay, and this when this is order of 1, its potential minus this is not its potential decay anymore. Okay, there's a fixed variable number, and this fixed variable number is what? Is a become function of, okay, you cannot neglect this. Okay, you cannot, so you have to take this into account into the solution form of our uy here. Okay, our uy here. So within the boundary layer region, we didn't discuss here, but if you consider that, will be have a function of y. Okay, function of y. And then sometimes this function of y is not. It will be what? Will be also like this, as you can see here. Okay, sometimes you have the forward flow here. Okay, and then, but you have a within the boundary layer you have a forward flow, but in the core region you have reverse flow. Sometimes you have happen like this within the pulsating pipe flow. Okay， 有时候这个地方你会看到，在 boundary layer 区域它可能是往前流的 ，OK， 然后在 core region 是 OK 回流的。It happened here. Okay, some instance. Okay, and then if you are Professor Miao student, is anybody is a Professor Miao, J.J. Miao student? Okay, he's study the pulsating pipe flow in the basement. There's a pulsating pipe flow experiment there. Okay, and they try to study the what the transition of this pulsating piping flow, right? So the transition of pipe flow, okay, because this kind of flow pattern, we have a pipe flow like this, and this is flow pattern is forward and backward. Is in the experiment they don't have any backward pressure. They only have a forward pressure, but it's an unsteady forward pressure. The all positive. Okay, that means the dpx is a positive number. Okay. So flow is always forward, but however forward pressure gradient has a large and smaller, large and smaller. Okay, and as you can see here, as I mentioned here, you may have this case. Okay, for this case you may have this, right? You may have this. We have a flow like this, the different direction. So here we have an inflection point. Okay, and this is inflection point in the hydrodynamic instability analysis. Once you have a flow velocity profile with the inflection point, it's most unstable case. And there's a lot of disturbance will be generated here. Fluctuation will be generated here. And this fluctuation can lead to so-called from laminar to turbulence source. Okay, and that will be a different story. Okay, later if you study the hydrodynamic instability, okay, there's one additional course called the hydrodynamic instability. You will learn that. Okay, what kind of flow is steady and what kind of flow is unsteady. Okay, and then from the laminar to turbulent, they call the transition process, and this transition process maybe is due to the hydrodynamic instability. Some of the instability analysis can give you some information about that. Okay, so that will be for the pulsating pipe flow, okay, this is always is an example, okay, so you should familiar with all these basic flow pattern, okay, this is once you go to very complicated flow pattern, you always go back to this simple, because this is very precise and we have exact solution for this, and a lot of physics can be catch from this, okay, a lot of physics, okay, 所有的物理大概最简单的问题都包含。Okay, so that will be for the pulsating pipe flow. Is any problem here? Okay, for the concerning about the pulsating pipe flow. So we just finished the pulsating flow. Okay, this flow. Okay, discussion here. Okay, so next we would like to go into so-called stagnation point flow. Okay, stagnation point flow. This is also an example flow. That means a lot of flow field is related to the stagnation point flow. What kind of flow field is related to the stagnation point flow? You can see inside, outside our jet engine there's a lot of stagnation flow pattern inside that jet engine. Okay, so if you see that jet engine outside or inside a lobby of our department, okay, we have a combustion chamber, right? And then once you will flow through the compressor, right? And compressor give you higher pressure, right? And then before the higher pressure means you become slow down your velocity. They will enter the combustion chamber. In combustion chamber, we need to have a so-called frame holder. Okay, and then if you take the one of jet engine like a Ch7, okay, Ch7 这个引擎, the end of the end section we have this kind of frame holder like this, okay, and we have a flow like this. And this is once we have this is called a frame holder. And what do you call the frame holder? This means we have combustion will be happen here because we would like to. If we don't have this, okay, combustion cannot take place because our high velocity may extinguish our combustion spark. Okay, so we need to protect this. Okay, protect this like this. Okay, you can see a lot of, so we have a flow, okay, with some kind of protection, and we have a spark here. And then once we have spark, ignition here, our flame can be happen, so combustion can take place. Okay, so that's one kind of, so as you can see here, flow impinging on a very near here this region, right, enlarge this region, okay, come like this, right, and flow is like this. And here we enlarge this region, it's almost flat. So this one is called a stagnation point flow, which is near this region for stagnation point. And why this stagnation point flow is very important? Because of a lot of material damages from this point. Okay, temperature is the highest point is this point. Okay, so material will start to damage from this point. If you don't take into, if you don't have okay, like if you don't have detailed information of here, okay, you are able to kind of control this kind of design. So we have to, for this kind of flow, called stagnation point flow. So then we have a flow, okay, impinging on the flat plate, and the flow will be starting moving, okay, sideward, okay. So this kind of flow we call a stagnation point flow. Then a lot of the flow, okay, condition or the reaction flow is based on this stagnation point flow condition. Okay, I think we will stop about 10 minutes. After 10 minutes, we can go back to talking about this. Okay, what's the exact solution for this? You can take a look outside the jet engine. I can show you if you are interested.